Okay, so we're going to look at accelerated reference frames, but now instead of being on a flat surface, we're going to work up to actually being on a sphere. Now, if we look at the Earth from the side, this is the North Pole up here, and the omega vector will be pointing like this, as the rotation is from the west toward the east in a right-hand sense. So the rotation's going this way. Now, the value of that angular velocity is 2 pi over the period, and of course a period is a day, which is 86,400 seconds, so you get a relatively small value, 7.27 times 10 to the minus 5 radians per second for that angular velocity. Now, if this is an object on the surface of the Earth, it's going to experience weight. That will be an mg force towards the center of the Earth. There. Then it will experience a centrifugal force directly away from the axis of rotation. It will finally experience Coriolis force, but that's going to depend on what the direction of the velocity is. So if this is the latitude lambda, and this is the radius of the Earth r, let's draw it down here. That's r. Then, yeah, this is the mg force. And then this will be the distance away from the rotational axis, and that's clearly going to be r cosine lambda. So the centrifugal force is, oh, that's horrible. The centrifugal force is m omega squared times that perpendicular distance, r. And that's m omega squared, radius of the Earth, capital R, cos lambda. Okay, we won't put the Coriolis force in here because it depends on the direction of the velocity. Now, we've seen that centrifugal force has a fairly small effect. So if we're at the equator, then let's look at the Earth from the North Pole, and we know that at a point close to the Earth's surface, the gravitational field G is just 9.81. The centrifugal effect will be directly away. That'll be omega squared r if we're at the equator. So the resulting gravitational field is just made a little bit smaller by the centrifugal effect in the accelerated reference frame. Because omega is so small, after you square it, even though the radius of the Earth is significant, it's 6 million meters, you end up with a fairly small correction here to the gravitational field. And that correction gets smaller with latitude. So here we are at latitude then. And what is the effect then? Well, the gravitational force is, of course, still just towards the center of the Earth. There's the mg force. And the centrifugal force is still directly away from the axis of rotation. And as we just saw, that's m omega squared r cos lambda. Now then, if you're standing on the surface of the Earth, there'll be a normal force then that's going to balance the two of them. I'm greatly exaggerating the angular deviation. The normal force is really going to be very close to being opposite to mg, just because the centrifugal force is so small on the Earth. Now, for the effect on the gravitational field, then, we're going to need to take this centrifugal force and find its components, because it's going to be partly outwards, and then it's going to be partly in the x direction in local coordinates. Now, if the latitude is lambda, then this is a corresponding angle, so we see we actually have a cos lambda component there that's going to be outwards. So the local gravitational field at latitude will be centrifugal force cos lambda, and then I'm just dividing by mass. I'm taking the force and dividing by mass. So because the centrifugal force itself has a cos lambda term in it, so this is omega squared r cos lambda, when you take the component along the outwards radial direction, you're going to end up with cos squared lambda. And so depending on the latitude, you can have up to a 0.036 effect right here at the equator, but the effect gets smaller with latitude as the angle lambda increases from 0 up to 90 degrees. Now we're going to do two calculations, sort of geophysical calculations using the centrifugal force. The first is we'll look at the shape of the Earth. We know it's not a perfect sphere. The surface actually is going to, if we imagine that it's a fluid, we know that it'll bulge a bit at the equator due to the rotation of the Earth. And the surface will actually be an equipotential surface. So a surface of constant potential energy is called an equipotential surface. And the reason that we're looking for an equipotential surface is if you had, say, if you didn't have equal potential energy over the whole surface, say if the potential energy was a little higher at one point relative to the other, then there would be a force there, and there would be a tendency for the higher potential energy bit of matter to flow towards the lower potential energy bit of matter, because we've seen that force is a gradient of potential energy. So given that once you have an equilibrium distribution of mass, it must be that the potential energy is everywhere constant over the surface, otherwise it would be changing. Now, gravitational potential energy, you recall, is inversely proportional to the distance. So we're going to look at the outer surface. Let's pretend the Earth was totally covered with liquid water. And so let's use big R for the radius of the Earth here. And then this will be the potential energy of the outer surface. Here's big M, and then here's a little bit of ocean water here, little m, a distance big R away from the center. Now, because we're in a rotating coordinate system on the surface of the Earth, there is a centrifugal effect. There is a centrifugal force, m omega squared r, and we want to come up with a related potential energy for that. Well, we know that the force is the gradient of the potential energy, the negative derivative of potential energy. So we've got to, when we differentiate potential energy, we've got to get this force. So we can just do the antiderivative of this, and the antiderivative of r is r squared over 2. So that suggests that we could use this potential energy, excuse me, as the one being related to the centrifugal force in the accelerated reference frame. Now, little r, of course, is the distance to the rotational axis, and when we view this from above, we remember that big R is the radius of the Earth. This is little r right here, and so that's r cos lambda. So for our potential energy, total potential energy, we'll have the gravitational, and then we'll have a centrifugal quasi-potential energy. Just like this is a fictitious force, this is the related fictitious potential energy. And we've substituted in for little r, we've substituted in r cos lambda, where lambda is the latitude right here. And where that's the equator. Okay, now we're going to say that r is actually not a constant, and it varies a little bit over the surface of the planet. We'll break it up into a constant part and then a variable part. So we'll replace that in here, and we'll get the following expression then for the potential energy. Give myself more room. So it's negative G, big M, little m, over R plus epsilon. Big R is a constant, epsilon's a variable, minus 1/2 m omega squared, cos squared lambda, R plus epsilon squared. Now epsilon's going to end up being a function here. It's going to vary over the surface. Now, next with that, we're going to do a bit of algebra here. I'm going to take out an R. That's going to leave me with a term that's 1 plus epsilon over big R. And then I'll just expand this bracket. Big R squared plus 2 epsilon R plus epsilon squared. There we go. Now we're going to use something known as the binomial approximation. You see, we expect epsilon to be very small here. Because of that, very small compared with R, because of that, we can approximate 1 over 1 plus epsilon over R using the first term in the binomial expansion. Now, the binomial expansion tells us that 1 over 1 plus x is approximately 1 minus x. So where we had GMM over R, and we had this term in 1 plus epsilon over R, we're going to say that's approximately GMM over R times 1 minus epsilon over R. And so it's no longer in the denominator. So this is just the leading term in the binomial expansion. This actually goes on forever. The next term would be like plus x squared over 2. All right, so making that replacement, we get this expression then for potential energy. This is the potential energy of a little water element. And if we expand that then, just by distributing here and distributing here, we get a total of 2 terms, 3 terms, 5 terms. So here they are, 1, 2, 3, 4, 5. Now, it turns out, though, that there's a couple of terms here of order epsilon. Okay, we're going to compare these two. And this one, it's GMM over R squared times epsilon. This one is M omega squared R cos squared lambda times epsilon. Well, it turns out that this is a gravitational force on the water element, and this is the centrifugal force on the water element, and the centrifugal force is much smaller. Okay, so because the gravitational exceeds the centrifugal, we're just going to drop this one. This just makes our algebra easier, and it preserves the highest order effect. We're then going to say that epsilon is pretty tiny. Remember, epsilon is the variation from circularity over the surface, and compared with big R, it's really tiny. So we'll drop this one as well, because it's of order epsilon squared. Now, we are again looking for a surface of constant potential energy, because that's what the equilibrium shape of the Earth should be. So let's call that constant potential energy U0, and that's defined down here. What we want to do now is we want to solve this equation. Remember, we've dropped these last 2 terms there. Okay, so when we solve for epsilon, we'll keep this term by itself, and we'll bring this term over and this term over. So we'll have U0 plus this term, G big M little m over R, plus this term, M omega squared R squared cos squared lambda. So all of that's now over here. And then we're trying to solve for epsilon. So we're just going to cross multiply up the R squared and cross multiply down the G big M little m. Now, this is a constant. That's the constant of constant potential energy over the surface. This is a constant value because R is a constant. So, and then when you multiply by this thing, it's also constants. So we end up with something that's a constant. And then this term here, which varies with latitude, we end up with a half. And then little m cancels, and then we get omega squared r squared. This term here, I'm just going to bring it down to the denominator, so it'll be gm over r squared times cos squared of the latitude. Now, the reason I left that r squared down here is, of course, that's the gravitational field strength at radius r. So I can say that epsilon is a constant plus 1/2 omega squared r squared over g cos squared of the latitude. Now, this is actually related to the centrifugal acceleration in some way, too. Omega squared r would be the centrifugal. So you could say, in a way, that this is the ratio of the centrifugal acceleration to the gravitational, but I won't bother. So this is what I've got. Now, I haven't said what this constant potential energy is yet, so this C is to be determined still. The way that we're going to do that is by setting a normalization condition, where we're going to say that this epsilon, the deviation from circularity, should average to 0 over the surface of the Earth. So if we do a surface integral of this, we want to get 0. Now, oh, okay, yeah, that's just recopying what we just had. So it looked something like this, except we were writing it down here. We want this to integrate to 0 over the surface. Let me have a look here. Here it is, yeah. No, this slide is like a ghost slide. Ignore that, because it's all on here. All right, so now, we're integrating over the surface of the sphere, so the Jacobian, the little element of area on the surface of the sphere, is sine phi d theta. So integrating with respect to theta, it just does a lap, 0 to 2 pi. Phi goes from 0 to pi, so that's the pole, that's the south pole, that's the north pole. And then we're going to have constant plus omega squared r squared over 2g. Now here, of course, we had cos squared lambda, but the latitude angle is measured from the equator. The phi angle is measured from the pole, so that means they're always going to be complementary with each other, adding up to 90, and that means that the cos of lambda is the same as the sine of phi. Because, well, you can prove this if you want. The cosine of 90 minus phi, which is what lambda is, you can use the angle sum identity and show that that just equals sine phi. So where I had cos squared lambda here, I'm going to replace it now with sine squared phi. Now all of that will get multiplied by the little bit of area on the sphere, which is sine phi d theta. Okay, so we've got a little integral to do. Well, the theta integral is nothing. That just gives us a factor of 2 pi. We've got to integrate the constant c over the surface. C just pulls out, and then we end up integrating sine phi d theta. And then that just ends up being the surface area of a unit sphere. So that's just 4 pi c. Then in the second term here, again, the omega squared r squared, that's a constant, so that gets pulled out. And then we end up integrating sine cubed of phi d theta. Now the integral of sine cubed, you write that as sine squared sine, then you use the sine squared identity, 1 minus cos squared, to express it as follows. And then you split that into two integrals. The first is the integral of sine from 0 to pi minus the integral of cos squared sine from 0 to pi. Now that is, of course, this one just integrates directly. The integral of sine is negative cos from 0 to pi. With this one, we need to take another step. I'm going to bring the minus in and join it with a sign. And now this is like a u squared du because the derivative of cos is negative sine. So the antiderivative of this one is u cubed over 3, i.e. it's cos cubed over 3 from 0 to pi. So putting in pi, you get minus minus 1. Then subtracting negative 1, you get minus negative 1. Here, cos cubed of pi is minus a third. And then you subtract cos cubed of 0 over 3, which is 1 over 3. So putting it all together, you get 2 minus 2/3, which is 4 over 3. So integrating sine cubed from 0 to pi gives us 4 over 3. Then we still have to do the theta integral, doing a lap, so that's going to give us a factor of 2 pi. So what we arrive at then, I'll just bounce back and use a little bit more space down here. Oh yes, right here. So we've got from our normalization condition that we want this to integrate to 0. Sorry, we were just having a spasm there for a second. So our normalization condition, we want this to integrate to 0. And this first integral is just 4 pi c. So now, zero is going to equal 4 pi c from the first integral. And from that second integral, we're going to have omega squared r squared over 2g. We get a 4/3 from the sine cubed integral. Then we get a 2 pi just from doing a lap with theta. So lots cancels out here. 4 pi, the 2 cancels. And then we end up with this expression for that constant c, so that epsilon averages to 0 over the surface of the sphere. So thus, epsilon equals this constant plus a term like this, varying with the cos squared of latitude. Now you can see that both of these have got r squared, omega squared, r squared, and a g in common, so we factor that out. And I'll take out a 6 to make a common denominator. Taking out a 6 leaves me with 3 cos squared lambda, and taking a 6 out of here leaves me with minus 2. So this is an expression for the variation from circularity over the surface of the Earth. And it varies with the cosine squared of latitude. Now, r plus epsilon is the distance from the Earth's center. So here's r. So this would be a sphere of radius r. And then what's going to happen is, if this is the pole and this is the equator, you're going to find something, and I'm greatly, grossly exaggerating this effect. So this will be r plus epsilon at the equator, and this will be r plus epsilon at the pole. And clearly epsilon at the pole will end up being a negative number, because at the pole the latitude's 90 degrees, so it's 3 times 0 minus 2. You get a negative 2 term out of the bracket. Okay, so we get a nice equatorial bulge out of this analysis, as expected. And you can work out the difference in radius between the pole and the equator, and it works out to about 11 kilometers, which is not quite the right answer. It's more like about 20. But there's other things we have to consider. First of all, g is not constant over the surface anymore. And so there's a bit more to go to the model, but we've made a decent first step. And we have shown that this will be an equipotential surface of equipotential energy. So it's not a perfect sphere, because of the centrifugal effect and a little extra potential energy term, there's actually a bulge there. So that's the problem we wanted to do related to centrifugal force. Next, let's talk about the Coriolis force and a couple of effects associated with that. First of all, back on the surface of the Earth, our omega vector, when viewing this from the side, points upwards through the North Pole. And we've got our little coordinate system here. And if you remember, the z-axis points radially outwards, and the x-axis points along the surface like this. And we just want to express that omega vector in terms of those local coordinates. What are its components? Well, if we bring the vector over here like this, the omega vector will be pointed up in that direction. So we can see it's going to have a positive z and a negative x component. If the latitude is lambda, then that angle there corresponds. So this will be the complement of lambda. So this angle here will be lambda. So we can now find the two components of omega. We see it is omega cos lambda, in the negative I direction. That's horrible. Omega cos lambda in the negative I direction. And then it's omega sine lambda in the positive k direction. Now, we need omega in local coordinates because for the Coriolis force, we have to do a cross product of v cross omega. Because remember, the Coriolis force is 2m v cross omega. So if we had vx, vy, vz, then we would get for our cross product 2m. Now for the I component, it's going to be vy omega sine lambda. That'll be the I component. For the j component, you're going to get two terms, vx omega sine lambda. So it's going to be vx omega sine lambda, and then minus minus, so that'll be positive vz omega cos lambda. Those will be in the negative j direction. Then in the k direction, you just get negative negative, so positive vy omega cos lambda k. So there, for an arbitrary velocity, is the cross product. This would be the Coriolis force. Let's consider a specific case. Let's imagine that we just have a negative x component for our velocity. So this is our velocity. So we're firing a projectile towards the North Pole. Now, the Coriolis force, well, it's going to be the direction of v cross omega. With omega pointing like this, we could see that omega is partly perpendicular and partly parallel to the velocity. So by the right-hand rule, we know that the force is going to be perpendicular to those vectors. If you point your right-hand fingers in the direction of v and then curl them towards the direction of omega, your thumb should be pointed into the page. Into the page, away from us, is in the y direction. So just by doing a cross product with our hands, we expect a deflection in the plus j. Well, let's actually do the cross product then. So the Coriolis force will be 2m v cross omega. So that's 2m, and we set up the determinant method for doing the cross product. These are our velocity components. It's in the negative I direction. And then this is the value of omega in our local coordinates on the surface of the Earth. Now when we do this cross product, we get nothing in the I direction. In the j direction, we get negative negative v times omega sine lambda in the j direction, and then the k component gives us nothing. So it's in the positive j, as we predicted above, or on the globe surface, it's towards the east. So if you're here and you shoot a projectile towards the North Pole, it won't actually go towards the North Pole. It will actually be deflected towards the east. Now we want to try and reconcile that with observations in the inertial frame. And here's how we do that. First of all, we notice that at the equator you're further from the axis of rotation than, say, here. That means that the points on the equator are actually going faster than the points here on the surface, because this point is closer to the axis of rotation. And as you get close to the pole, the velocity gets smaller, and then it's basically zero at the pole, because the velocity depends on the distance from the rotational axis. So if we view this perhaps in side view, omega's coming out like this. The velocity here is going to be fastest. And then the velocity here, again into the page, is slower. Why is it slower? Because it's closer to the rotational axis. When you're here at the equator, you're much further from the rotational axis. Now let's pretend that L is our launch point and T is our target point. And let's draw those on the surface of the sphere. Again, okay, so L is our launch point and T is our target point here. So L is here, and then T is up here. So we are going to fire this projectile towards the target, so it's going to be moving in that direction towards the target. But of course the launch point and the target point are both moving because they're on the surface of the Earth. But the launch point is actually going to be moving faster than the target point is. So these are the v equals r omega speeds, and then this is just the firing speed. Well, because of that, the particle, the thing that we're firing, the projectile, is going to gain ground on the target. So the target might move from here over to here. So this was the initial location of the target, and then this is the final location of the target. So this is just due to the rotation of the Earth. So I'm probably exaggerating the distance that it would actually travel. But for our launched object, it's going to be going faster, so it's going to travel necessarily further than the target went. So relative to the surface of the Earth, this projectile that you shot straight, right, it was aimed directly at the target, it's actually deflected to the east. So the launched particle has a greater speed. Now, in our local coordinate system, this is in the y direction, right? So this would be the y-axis. So we're looking down from above, so the y-axis is to the right. So the launch point has a greater speed in the y direction than the target, due to v is r omega, and being at a greater distance from the rotational axis. Now, another example of that is in the northern hemisphere. If you have a region of low pressure, then the winds will flow inwards towards that region of low pressure. Well, if they flow in from the south, they're going to gain ground on that low pressure and be deflected to the right. If they flow in from the north, then they'll be going more slowly than the ground is where under the low pressure region, so they'll be deflected towards the west. So that means that if you've got a low pressure center here, the winds actually, as we've just seen from our Coriolis argument, circle around it in an anti-clockwise or counterclockwise sense in the northern hemisphere. If it was a high-pressure system, we could just run through the analysis again, and we could say the outflow winds here would fall behind the equator, and the outflow winds here would be deflected to the east, so that the circulation of winds around a high-pressure system is in a clockwise direction. So that's just the Coriolis force. Here's another problem. Let us now throw a particle straight up and think about what's going to happen to it. So we're looking down from above, down onto the pole, so the omega vector is pointing towards us. So this is the local y direction, this is the local z direction, and then here's the velocity of the particle. There's the rotation sense. Now the local gravitational field is modified by the presence of the centrifugal force. And so if we're at latitude, that will be omega squared r times cos squared lambda. But if we're at the equator, then that term just disappears. Now, in the inertial frame, so if you weren't on the Earth, if you weren't rotating with the Earth, then you're going to say, okay, that projectile that you're shooting has a speed v naught, and it's also got a speed of r omega due to the rotation of the Earth. So it's going faster because of the rotation of the Earth. And as a result, the particle is not just going to go straight up and straight down, it's going to travel in sort of planetary projectile motion and then land over here after the Earth is rotated a certain distance. And that's a complicated enough problem. In the accelerated frame, what we find is that, and actually in the inertial frame too, as we'll explain later, when you shoot this thing straight up, it doesn't land directly where you threw it from. It actually is going to be deflected to the west. It's going to fall behind you a little bit. Now, in the accelerated reference frame, we can explain that from the point of view of the Coriolis force, because if you do the cross product of v cross omega, you'll see that our Coriolis force ends up in this direction. So point the fingers of your right hand in the direction of the velocity, and then curl them towards omega, and you get a right-hand rule force that's in the negative y direction. And we'll explain later how to reconcile that with what goes on in the inertial frame. It's a little bit harder. Now, that Coriolis force in general is quite small. And it's always going to be perpendicular to the velocity, but let's just ignore any components there and say basically in the z direction we have projectile motion, and the Coriolis force is just creating a small sideways deflection for us. So because it's projectile motion in the z direction and nice constant acceleration, we can just use physics 11. And that gives us the displacement in the z direction. And we can factor a t out of that. That'll be useful later on. And then we can ask the question, okay, if you go all the way up, and then come back all the way down, that's obviously zero displacement. And if you solve that for time, then you're going to get two answers. Either time is 0, or this bracket is 0, and that bracket being 0 gives us a time of 2 v naught over g prime. That's when you're back at the ground. So that's your total flight time. Now, as a function of time, the z speed, it's just projectile motion speed, so it's v initial minus acceleration times time. And we need that expression because, of course, the Coriolis force depends on how fast you're going. So what is the force? Well, the Coriolis force is 2mv cross omega. We did the right-hand rule above, but let's just verify by a cross product that we get a consistent answer. So our velocity now is just in the positive k direction. So we put in minus omega cos lambda, and we put in omega sine lambda for the components of omega in the local coordinates. And when you do that cross product, there's nothing in the I direction. In the j direction, you get this term. In the k direction, you get nothing. So it becomes 2m, and then it's going to be minus, minus, minus. So overall negative. It's going to be vz omega cosine lambda j. So it is in the negative j direction, as we discovered from doing our cross product. Now, for the acceleration, that's just the force over mass. So basically, we just lose mass. I'm going to take this opportunity to substitute in my time expression for Vz. It's V naught minus G prime T times omega times cos lambda in the j direction. So that's the acceleration. That's in the y direction. Remember, we have projectile motion in the z direction and a small Coriolis displacement sideways. We're now going to find the y speed and the y displacement by integrating this time-dependent acceleration. And I'm going to do it at the equator from here on in, substituting in 0 for the latitude. So basically that cos lambda term just disappears. So dv is a dt, and I integrate. The y velocity starts off at 0 at the initial time of 0. So this is an easy time integral to do. There's a bunch of constants, 2 omega cos lambda. Then we get this part here that actually depends on time. So this side, you just get Vy minus 0 or Vy. Here you get minus 2 omega. Oh, I said I was going to drop the cos lambda, didn't I? Yeah, so that's just equal to 1 now. So the minus 2 omega comes out, and then you get V naught t minus G prime t squared over 2. And so that's the sideways velocity in the negative j direction. Now, for the sideways displacement is v dt. I just integrate this velocity with respect to time. And for my y displacement, I get minus 2 omega. This becomes v naught t squared over 2 minus g prime t cubed over 6 in the j direction. Now, when the thing is back at the ground, we can figure out, because we know what the time is when it gets back to the ground, you can show that the y displacement is 4/3 omega v naught over g cubed to the west. So last class we said if you drop a marble down a deep mine shaft, it'll be deflected by the Coriolis force, and it'll be deflected to the east. Now we're saying if, on the other hand, you throw it straight up, it will actually be deflected to the west. Now, explaining that in the inertial reference frame is a bit of a challenge, and we'll pick it up at that point in class.